Okay, so welcome to the course of signals and systems. So let's start with the name first. Name of the course is Signals and Systems. So today in this introductory lecture, I will focus on signals. For the next two classes, I will be discussing what is meant by the signals, and then in the next unit, we will move towards what is meant by the systems, right? So to start with the term signals or signal, so let me write it down here. Signal. So what is or how can I define a signal? Any idea? How can I define a signal? What is signal? What should have been the definition for a signal? Since you have zero knowledge on signals and systems, so that's why I start from the very basic. What is meant by the signal? How can I define a signal? Input. Sending a message, okay. Any other answer? One answer is input, second answer is sending a message, then
any expression that gives us information.
Expression
That gives us information.
Expression that gives us information, okay.
Carrying
information. So basically, any other answer? So basically, we can recognize the signal as an attempt to communicate information. Somebody has told, sending information, sending message. So signal can be defined as, at the very basic level, signal can be defined as an attempt to communicate the information. So long back, say 1,000 years back, during the war times, so there is a kind of something is being shown. For example, how many of you have heard about Satyajit Ray? Only few, no? Satyajit Ray, you have heard, no? Have you ever seen any of the movie directed by him?
Yes.
Have you ever seen the Hirag Raja Deshe?
Yes.
You have seen, no? So in that particular movie, it was shown that at the night time, some fire will be shown to Gupivanga so that they can identify that something is going over there. So that can also be regarded as a signal. In ancient times, the name signal came from the signaling or sanket. All of you have heard about the traffic signaling. All of you have experienced traffic signaling. So what is that? Basically, it's a kind of a sanket, right? So not only the attempt to communicate, but also signal means an attempt to store, to record, and to communicate the information. So in ancient times, I can say that signal is an attempt to communicate the information, but now I can identify or I can define the signal as an attempt to record. First of all, you have to record the signal, you have to store it for some processing application, and then the communicate information. So that is all about the signal. Signal means an attempt to record, to store, and communicate information. Okay. So right at this time, what I am doing actually, I am basically transmitting signal. From this dais, I am basically transmitting a signal. Isn't it? What I am doing? I am recording my lecture. First of all, I am generating some audio piece. I am generating some audio piece related to this particular subject, right? Then what I am doing, with the help of this particular smart board, I am recording not only this audio piece but also these visuals. Okay, these visuals, what has been written on this particular board, this is also stored. In addition to my voice, in addition to my speech signal, this entire thing is also being stored. Okay, so I am recording something. First of all, I am recording something, and this is being stored in the internal drive of this particular device. Later on, I can also disseminate the same thing to you people or to other people through some media. So basically what I am doing right now is basically I am generating a signal. So everything can be thought as a generation of signal if that particular phenomenon can be associated with this definition. An attempt to record, store and communicate information. In ancient times, only this communication part was there, as I told you. Long back, during the war time, suppose there are three types of flags, right? Three types of flags. One is red flag, second one is white flag, third one is yellow flag. Even during the time of Mahabharata, you have three different types of flags. Okay, that means what? If red flag is being shown, that means this is a signal of what? Signal of what? Red flag means what? Signal of what? White flag means what? Signal of peace. And yellow flag means what? Signal of? Sorry? Signal of friendship. Right? That means that there should be a collaboration between two such countries. Okay. So during that time also, just by using three different colors of flag, red, white and yellow, you can communicate something to the other people. The persons from one country, they can communicate some information to the persons of other country. King of one country to king of other country. So that is all about the communicating the information. That is also signaling, sanket. You have the traffic signal, red, yellow, and you have the different meanings for each of these three different colors. Red means what? Stop. Green means what? Go. Yellow means what? Wait and watch. Wait and watch, and then you proceed. Isn't it? So, communicating information was very basic thing associated with the signal. Then, as the technology evolves, then you have these other two attributes associated with the signal. First of all, the recording part. Previously, the recording part was not there. Previously, say 1000 years back, you don't have this recording option. Isn't it? At that point of time, you don't have any book. You don't have any audio clip. You don't have any video lecture. 1000 years back. Okay. So only communicating information. During the time of Veda, at that time, you have to hear something and accordingly you have to memorize. There was no such book available 1000 years back. But with the advent of technology, what we have the provision of recording something. Recording in the form of hard copy, recording in the form of some books. And over the last few years, last 10 years or 15 years, now you have the e-copies. You have e-books, right? You have now you have these audio lectures, the video lectures, everything right at this point. So with the advent of technology, the recording and the storing, these two attributes are also added to the basic definition of signal. But all of them can be categorized to the basic notion of signal. Right? So that is the definition of signal. Is it okay? Fine. So now, from the philosophical perspective, now let's, as I've already told you, that this particular class or this particular course is a mathematical one. But apart from doing the mathematics, you have to also understand the philosophy behind it, rationally behind this mathematics. You can do some mathematics, but what is the basics of this mathematics? You have to understand, right? So now let's, after you understand this basic definition of signal, now let's move to define signal in a mathematical background, right? So mathematically, what I can say is that this signaling or signal can be visualized as a mapping. In the first slide, I have mentioned what is signal, the philosophical perspective, and now let us define the signal from the mathematical perspective. And gradually, you will see that this philosophy and the mathematics, they go side by side. There is no collision between the mathematics and the philosophy. Engineering and philosophy, you might think that okay, philosophy is a humanities paper and we study engineering or electronics engineering, so there is no such correlation, there is no such connection between the philosophy and the mathematics, or philosophy and this engineering. And gradually you will see that this philosophy is there everywhere. And one of my friends told me that yeah, philosophy is there everywhere, and that's why the highest degree in academia, the highest degree, what is the highest degree in academia? Anybody have any idea? What? Yeah, PhD. So what is that? What is the full form of PhD? Huh? Right. This PhD stands for philosophy. So no matter whether you are from engineering background or commerce background or science background or humanities background, the highest degree, ultimately everything converges to philosophy. Doctorate in philosophy. In this. Doctorate in philosophy. In that. Right. So ultimately everything converges to philosophy. So in the first slide I have mentioned what is signals in philosophical term, and now let's make it mathematical. So what is that basically? So signal, I can visualize signal as a mapping. Signal, so now signal can be visualized as a mapping from a domain to a codomain. Mapping from a domain to a codomain. So suppose this is one domain and this is a codomain. So let me mark this as domain and this is the codomain. So now you understand now what is meant by a function or mapping. So you have one particular element over there. Suppose there are so many elements are there in the domain set. Set you understand, I believe. You understand what is meant by set. So in one set you have so many elements. Suppose let's start with a few elements, 5 or 6 elements. That's the domain set. And there in the codomain set you have few other elements. Now signaling means what? Signaling means basically the mapping from one domain, one set to the other set, from the domain set to the codomain set. So suppose, this maps to this point maps to this point. It is not true that it is always a one-to-one mapping. It could have been a many-to-one mapping as well. For example, this point can also be mapped to this point. This point can be mapped to this point. And this is the mapping. Right? So here you have one domain set, here you have another codomain set. And signaling or signal means a mapping. Mathematically I can say that signal is a mapping from one domain set to one codomain set. Okay? And this mapping is not always a one-to-one. It can be one-to-one, but not necessarily one-to-one mapping. It can be many-to-one mapping. Right. And what about these defined elements? So you have so many elements over there. You have one element there, one element there. So these elements, so you understand, you have studied, hopefully you have studied vector. You understand what is meant by vector. You know, na? Scalar, vector, you know the difference. So these elements, so elements in the domain set, so they can be a single dimensional or can be multi-dimensional as well. Similarly, the elements in the codomain set can be one dimensional, can also be multi-dimensional. So based on that, we will define a one-dimensional signal and the multi-dimensional signal. One-dimensional signal, two-dimensional signal, three-dimensional. Beyond three, you cannot just visualize. Max you can visualize 3 dimensions. You cannot visualize 4 dimensions, 5 dimensions, 6 dimensions. So hypothetically, it is possible, but you cannot visualize. You cannot interpret the multi-dimensional beyond 3 dimensions. Okay. So most of the cases, we will in this particular class, obviously, we will deal with the single dimensional signal. But that does not restrict the bigger perspective of signal or signaling. Whenever I refer to signal, so signal means something, some entity which can have multi-dimension. Signal can have multi-dimension, can have 2 dimension, can have 3 dimension, can have more than 3 dimension as well. But for the sake of understanding, for the sake of simplicity, particularly in this course, we will restrict our discussion on single dimensional signal. That is the assumption. But that doesn't mean that signal is always single dimensional. I will give you some references, I will give you some examples where signal can be multi-dimensional as well. When you study the digital image processing signal, then you see that this signal is basically a 2-dimensional signal. 2-dimensional plus 3-dimensional. If you go for video processing, then it's a basically 4-dimensional signal. Okay, but in this sense, it's a very basic course, fundamental course. So in this particular course, we will restrict our discussion within that particular domain. Okay, we are dealing with only single dimensional signal, 1-dimensional signal. But it doesn't mean that signal is always 1-dimensional. Signal can be multi-dimensional as well. So here, the elements in the domain set can be multi-dimensional, and there the signal elements in the codomain set can also be multi-dimensional. But in our case, we will restrict ourselves to 1-dimensional to the another dimension. That is one thing. And then, as I have already told you, there is a mapping from this set to that set. And typically, so if I go even further, so I can call this like a mapping from a real set to a complex set. This is a one level more abstraction. You have started with the philosophical definition of signal, then you have considered the mathematical background of that, and now let's make it much more abstract. So we are doing this abstraction not to make life difficult, but to understand the concept much more elegantly. So it's a mapping, as I told you, mapping from one domain to another codomain. And this entire set in the domain set can be visualized as a set, this R, real number set, to a complex number set. So you know that any complex number can be visualized. If you have any real number, say 1, 2, 3, 4, any real, say integer or the fraction, for example, you can always visualize any real number as a part of the complex number. It is always possible, but the only part is 0. Right? Suppose the number is 1.3. This 1.3 can be visualized as 1.3 plus j into 0. That means the complex, the imaginary part is absent. So if you visualize the complex number, if you visualize any number as an element of the complex number, that means you are visualizing on a much abstract level. Okay. So signal, as I have told you, is basically a mapping from the real set, because that variable, it cannot be imaginary or cannot be complex here. But where you are mapping the codomain set, it can be complex as well. Now, if it is a 1-dimensional, then R to C. If it is multi-dimensional, then I can call it like r to the power n to c to the power m, something like that. So signal can be visualized as a function, from r to the power n to c to the power m. That means n-dimensional signal there, n-dimensional entity there, to m-dimensional entity in the codomain set. In the domain set you have n-dimensional entity, and in the codomain set you have m-dimensional entity. So n can be anything, but remember, since it's dimension, so n should be integer. N should be integer, and n belongs to what? Z plus, right? Similarly, n belongs to Z plus. Similarly, this one, m also belonging to Z plus. So that is much more abstract. So mathematically, if you are mathematically very strong, then you can understand what is that. Okay. Now, after giving this basic idea about signals and this shape theory concept, now once again let's come back to the very basic. Anyone in the class who have not understood this part? Basically, shape theory concept. Nothing more. Clear to everyone? Okay, fine. So in the first slide, what we have done, we have made this philosophical definition. The second slide, we have made it much more mathematical. Now, make it practical. Now, in our case, as I have told you, we will use in this course, obviously, we will use unidimensional, single dimensional signal. We will deal with the single dimensional signal, right? And in the domain set, you have seen that there are a few elements in the domain set, and these elements are mapped to some other elements in the codomain set. Now, the elements in the domain set, they are known to be the independent variable. Element in the domain set. These elements are known as the independent variables. And based on the values, so you can have, as I have told you, that there could be multiple dimension, 2 or 3 dimension possible over there. So based on the values of this and based on the mapping from here to here, something is obtained at the codomain set, and this is known as the dependent variable. So signal can also be defined as a mapping from the independent variable. So signal can also be defined as a mapping from an independent variable to a dependent variable. Independent to dependent variable. Signal can also be defined as a mapping from an independent variable to a dependent variable. Right. Now, in our case, mostly we will restrict. Once again, I am emphasizing on the term mostly. We will emphasize, or we will consider the independent variable as time. Time as the independent variable. But make no mistake, that time is the only one independent variable. Make no mistake. So whenever I ask the students about what is signal, many of my students have answered like this: signal is something which varies with time. Doesn't make sense. Signal can vary with time, signal cannot vary with time. Which is not varying with time, it can also be regarded as a signal if it falls under this category, an attempt to store, record, store, and communicate information. Okay. So that independent variable can be anything. The independent variable can be time, the independent variable can be space, the independent variable can be anything, can be temperature, can be pressure, can be everything, can be day, can be everything. But when we go into the deep of this subject, signals and systems, then we will consider the independent variable mostly to be time. Right. Apart from that, as I've already mentioned, that signal is a mapping from the independent variable to a dependent variable. So now you have to understand what is the, so I have given the name. One variable is the independent variable, second variable is a dependent variable. So let me go to this slide. Yeah. So basically you have independent variable there and two are dependent variable. As I've told you, most of the cases we will use the independent variable as a time. Now the thing is that what is the type of this independent variable? You understand what is meant by the continuous, you understand the continuous variation, you understand the continuous variation, you know what is meant by the continuous variation, do you know what is meant by the discrete variation? Discrete variation you also know. Anybody in the class who don't understand what is meant by the discrete variation, please raise your hand. Continuous variation you know? You know, huh? Continuous variation. Okay. I'm giving you some example. Say, if it is asked that today's temperature, outside temperature, suppose you know that we have an assumption something like that. The minimum temperature, outside temperature can be say 20 degrees centigrade, and the maximum temperature can be say 32 degrees centigrade. So minimum temperature, today's minimum temperature, outside temperature is 20 degrees centigrade, maximum is 32 degrees centigrade. Right. Now if you measure the temperature, outside temperature using appropriate device, the value could have been anything between 20 to 32. 20.1, 27.3, 29.93. If you are using very precise instrument for the measurement of the temperature, you can have like 3 digits, like 30.354 degrees centigrade. If you are precise. So it can assume any value within the set 20 to 30%. Right. 20 to 30, any number. So it is from a real number set. Real number set is these two values, 20 and 32. So the continuous value. Any value you can assume. So any value you can expect 20 to 30. On the other hand, suppose I would ask you, or suppose it is told that you have to find out the runs scored by any cricketer every calendar year. Runs scored by Virat Kohli in the calendar year 2021, 2022, 2023, 2024, 2025, something like that. Say in ODI, in T20, Test match. Right. So now the runs scored by any cricketer in any particular calendar year, or in World Cup, or in any particular championship tournament. So this is a number basically. It cannot be fractions. So runs can be 900, can be 1000, can be 1020, can be 1200, can be 1280, but the runs cannot be 1280.5. It cannot be like 1040.8. It is always from a positive integer set. It can be 0 also. Hypothetically, it can be 0 also. Isn't it? But it cannot be 293.7 runs being scored by Virat Kohli in calendar year 2023. It is never possible. The average run can be average score. Suppose he has played say 100 match in a particular year, and what is average? Average can be anything. But the total run being scored by any cricketer in any particular calendar year, it cannot be fraction. That means the run. So if I consider the temperature. So if I consider the temperature, so the temperature belongs to this set R, or I can call it R plus, positive. Typically in Kolkata, you don't expect the negative temperature, right? And if I call it run, this run belongs to set plus. So when I call it R plus or R, that means it's a continuous variation. And when I call it like z plus, right, it's positive integer. Positive integer, set of positive integers. 1, 2, 3, 4, 5, 6 up to 100, 200, 500, 800, 1000, 2000, go on like that. You understand the difference between the continuous and the discrete? Now, how can I identify whether this particular variable is a continuous or discrete? So, for discrete variable, for every variable, you have a neighborhood, and in this particular neighborhood, you have only one representative, only one value in that particular neighborhood, only one value in the neighborhood. If I consider discrete variable, so discrete variable is always associated with a neighborhood, and in each neighborhood, you have only one value, only one value in that particular neighborhood. That's all about the discrete variable. And in continuous variable, sometimes we also synthesize the discrete variable from the continuous variable. So that's why I have given that particular name. That we have to identify some neighborhood and you have only one representative. Then you have class representative in your class also. Right? You have class representative, so one person that will basically identify or that will basically represent the entire class. Okay. So with the discrete variable, you have always one particular neighborhood associated, and you have only one element identified in that particular discrete variable. Similarly, when it comes to the dependent variable, so that is all about independent variable. Similarly, when it comes to the dependent variable, so dependent variable can also be discrete, can also be continuous, right? Since independent variable can be continuous and discrete, similarly, the dependent variable can also be discrete and continuous. So now I have 4 different types of mapping. Can you get my point? I have now 4 different types of mapping. What is that? Something like that. Here you have, say, independent variable, and here you have, say, dependent variable. Okay. Continuous, discrete, continuous, can you get the point? I would like to draw something. Independent variable can be continuous as well as it can be discrete. Dependent variable can be continuous as well as it can be discrete. So you can have 4 different types of signal definition: continuous to continuous, continuous to discrete, discrete to continuous, and discrete to discrete. Is that point okay? I'll give you the example. Just try to understand the concept. Whether the concept is okay? Anybody who cannot follow, please raise your hand. Signal is basically mapping from a domain set to a codomain set. The variables in the domain set is known to be the independent variables, and the variables in the codomain set is known to be the dependent variables. Now, depending upon the type of the variables, so independent and or the dependent variables can be continuous or discrete. So since signal can be thought of as a mapping from the independent variable to a dependent variable, or variables to variables, or multidimensional case, so you can have the continuous to continuous variation, continuous to discrete variation, discrete to continuous variation, and discrete to discrete variations. Right? And then I will give you 4 practical examples of that. Right? So to start with, let's start with the example of continuous to continuous, continuous independent variable and continuous dependent variable. I don't want to start with time axis. Let's consider the pressure. Versus temperature. pressure versus temperature. This graph in any plant, say for example, how does it vary? Say this much of Pascal to this much of Pascal. That is a variation. It can have any particular value. Now that variation can be thought of as a continuous variation. And what about the temperature fluctuation? That can also be regarded as a continuous one. So pressure versus temperature or anything, say volume versus pressure. So you can consider defined system, and accordingly the variation can be thought of as the variation. So intentionally I have not used the very basic form of signal, and hopefully all of you know. T versus Vt, and if I draw the sinusoidal signal, all of you have experienced this one, no? In your lab. T versus sinusoidal signal, sine of omega t, A sine omega t. But in the very fast representation, I don't want to show you this particular depiction of picture of signal, because in case I do that, you have some false impression that signal is always a function of time. Signal is a function of time, but not necessarily always. Signal can be a function of anything, any independent variable. So my independent variable can be pressure. My independent variable can be pressure. And I find that as pressure increases, say I find that as pressure increases, the temperature drops. So the variation can be something like that in any plant. Now here I find this is the minimum value of the pressure, this is the maximum value of the pressure, this is the maximum value of the temperature, this is the minimum value of the temperature. Now within this minimum value, the pressure can assume any value, any number it can assume, any number. There is no restriction, there is no such neighborhood, any number. Here to here, for the temperature from here to here, you have any number, any fluctuation. So it's basically a continuous to continuous. That means your independent variable is continuous in nature, and the dependent variable is also continuous in nature. Right? And you have so many examples for this continuous to continuous fluctuation. So many examples. Okay. Now I go to continuous independent variable to discrete dependent variable. So now I have continuous independent variable and discrete dependent variable. Can you cite any example for that?
Sir, can I give an example of mathematical function? It is not related to physical quantity like volume, temperature. Like a GIF, greatest integer function.
Yeah, it's possible. It's possible. So, okay, that is great. So, let me give you some physical example of that. That is your independent variable. That means what you have given, like x versus x, something like that, right? X versus x, yeah, pretty much true. So, suppose my independent variable is a continuous one, and let's call this is basically I am plotting with respect to say 24 hours with respect to time. Let's call it time. Let's call it time. Okay, time. Say this is 22nd March. Nine o'clock. This is say 23rd March. 9 o'clock. This is say 24th March. 9 o'clock in the morning. This is time axis, right? So this is a continuous variation. There should be a continuous variation from, if it is 9 there, so 9, then 10 o'clock, 11 o'clock, 12 noon, 1 p.m., 2 p.m., and go on, something like that. Now can you identify something, some parameter which remains constant during that period of time?
Class period.
Huh?
Period.
Period means what?
Means a particular subject is done at the time.
Not exactly.
Whether
Or let's make it like, don't use 9 o'clock, rather make it like midnight. Let's make it midnight, okay. 22nd March midnight, 23rd March midnight, 24th March midnight.
It can be density of water.
Water? How can it be water?
That is
I've given you some hints. 22nd March midnight, 23rd March midnight, 24th March midnight. Something remains constant during 22nd March midnight, 23rd March midnight. Then it changes. Say for example, petrol price. Petrol price. That remains throughout during that period. And let's assume that the price can be represented in dollar, not in rupee, dollar. Say this much of dollar. So that is fixed. 22nd March, throughout 22nd March, this is fixed. Some dollar. Say presently what is the amount? Say 130. Then say 23rd March, 24th March, say this is 135. Then 24th March onwards, say this is 139, something like that. So here there is some certain assumptions. The assumption is that this price is in whole number. Cannot be $130.3, $130.5. I'm assuming 130, 131, 130 like that. And it remains constant throughout. So here the independent variable is basically the time. 22nd March midnight, 23rd March midnight. That is entire time. During this entire 24 hours, this your fuel price is kept constant. And that is discrete in nature also. You don't have 130.5, 130.7, something like that. That is constant also. So this gives you a mapping from a continuous variable to a discrete variable. Okay? Well, so now let's move to the third one. Discrete independent variable to continuous, discrete independent variable to continuous dependent variable. Can you give me an example? Discrete independent variable. Discrete independent variable to continuous dependent variable. Independent variable is discrete. Right. So there is a neighborhood and there is one representative in that particular. And continuous dependent variable. Dependent variable can belong to this R class. Let me move to the next slide. Discrete independent variable to continuous independent variable. Any guess?
Sir, for the independent variable, discrete independent variable, the domain is fixed, like the domain is real number.
Yeah, domain is always real number.
But sir, then it will not be a function.
Yeah, domain has to be real number. Huh?
Domain is real, but sir, for the some specific values, we are not getting the output. Like it is in discrete method.
What I'm saying is that discrete means what? So you have the, suppose this is your time axis or any independent axis, right? Let's call it time axis. Let's call it time axis, right? So 24 hours. Say let's start from 8 o'clock in the morning to say 4 p.m. 8 a.m. in the morning to say 4 p.m. in the afternoon. So you have how many hours? 8 hours? 8 hours. Now the time is continuous, 8 a.m. to 4 p.m., 8 hours. But I am finding out one representative in a particular neighborhood. Suppose I am dividing these 8 hours into say 8 neighborhoods. And there is one person, there is one time which is or who is the representative or which is the representative of that particular time zone. Suppose 8 a.m. So 8 a.m. is considered as one representative. The next representative can be considered to be say 9 a.m. Then comes say 10 a.m. and so on and so forth. So time is continuous, 8 a.m. to 9 a.m., 8 a.m. to up to 4 p.m. So 8 hours time to 40 minutes is continuous. But I would like to pick only one representative from that particular neighborhood of 1 hour. It can be 8:30, 9:30, 10:30, right? It can be say 8:45, 9:45, 10:45. So most of the cases we consider uniform kind of spacing. It can be non-uniform as well. To make our life simple, let's call it uniform spacing. 8 to 9, 9 to 10, 1 hour spacing. Okay. So since the election time is coming, so I'm giving one example of that. At every hour, let's find out what is the poll percentage in the last 1 hour. And suppose in the booth level you have to capture this and you have to send it to the election official. What is the poll percentage? It can be say with respect to the total electors. Suppose at 8 a.m. suppose somebody has reported that in the last 1 hour 7 a.m. to 8 a.m. the poll percentage, suppose this is 2.5%. Then at 9 a.m. they reported from 8 a.m. to 9 a.m. during the last 60 minutes the poll percentage was like say 6.8%. Then comes say 9 to 10, then it comes to say 10.1%, something like that. Right. So this is a kind of mapping from a discrete independent variable to a continuous dependent variable. Can you get my point? Can you understand what I am saying? You are not measuring the poll percentage every minute or every second. Rather, you are collecting the number of electors present within the last 60 minutes. Suppose there are 100 electors who have cast their vote, and you measure this with respect to total electors. Find out the ratio, and that gives you the characteristics of poll pattern within the last 60 minutes, and that you report, and then that you just communicate it to the election office. So basically, the signal is a continuous one. The variation is a continuous one, but you are measuring it at some uniform intervals, at 8 a.m., at 9 a.m., at 10 a.m., at 11 a.m., and so on. And you are measuring what is the, so once again remember I have mentioned the poll percentage, not the exact number of polls being cast. So percentage can be fraction as well, and it can be continuous, has to be continuous. Right. So say 2.5%, 8%, 10.1%, sometimes say 11.3%, then comes once again it drops to say 5.2%, something like that. So continuous variable, the y-axis you have, this is the poll percentage, there you have the time. There you have the time, and this is the poll percentage. Poll percentage. Okay. So discrete to continuous. And then the final one. Discrete to discrete. Can you give one example of that?
Balls scored to runs scored.
Number
of balls scored to total runs scored.
Number of balls
scored
to
total runs scored.
Yeah, that is also possible. I am giving another example. Yeah, that is also true. Say balls, and here you have the runs in a particular over, say for example. Right. So you have like 1, 2, 3, 4, 5, 6. So they are discrete in nature. You cannot have like 1.3 1.7, 2.9, never possible. Ball number 1, ball number 2, ball number 3, ball number 4, 5 and 6. If there are 6 balls in over. And then the run scored. That will be obviously discrete in nature, and both of them belong to Z plus. Suppose here you have 2, here you have say 4, then here you have say 0, 0 there, 0 there, then here you have say 6, something like that. So discrete to discrete. Intentionally, in all these 4 examples, except the third one, I have not used time. I have not used time. To make sure that, to emphasize that signal is not a function of time always. Signal can be a function of anything. Signal can be a function of time, signal cannot be a function of time. But obviously, in this semester, throughout, we will use the signal as a function of time. But in this particular class, the first class, make sure that signal can also be a function of, cannot be a function of time always. Right? So let us summarize what we have discussed for the last few minutes. Signal can be thought as a mapping, mathematically as a mapping from one domain set to one codomain. Right? So the elements in the domain set can be multidimensional. Elements in the codomain set can also be multidimensional. Right? And then the elements in the domain set can be those variables. They are typically known as the independent variables, and the elements in the codomain set, they are known to be the dependent variables. And as far as the type and the nature of the independent and dependent variables are concerned, they can be either continuous in nature or discrete in nature. So now you have 4 different possibilities: continuous, continuous mapping, continuous discrete mapping, discrete continuous mapping, and discrete. Okay. Is that okay up to this? Any doubts? Yeah.
So, in the case of discrete independent variable to
Continuous dependent variable, yes.
how can we say that because at a particular time we are having a specific or a particular code percentage.
Right.
So how is it continuous at that? It is discrete when at that particular time this much is the code percentage. Like the runs code with respect to balls.
Not exactly. I mean, to some extent, if it is fixed, because yeah, to some extent it is true that yeah, you may call it, it's not exactly continuous, because the denominator is fixed always. Denominator is always fixed. If the denominator is not fixed, if the denominator is a variable one, then you don't know that whether it belongs to R plus or Z plus. As far as the denominator is fixed and the numerator assumes value from the Z plus, so yeah, it should be, in that case it should be yeah, for fixed number of electors, then it should be discrete variable, not a continuous one. Yeah. Yeah, that's true. So now let's give you I'm now giving you another example. Forget about this pole percentage. So let's consider like average temperature, or say student roll number versus student CGPA. Roll number versus CGPA. That is continue. I mean, that student roll number is discrete one. You have 59 in your class. So discrete 1, 2, 3, 4, 5, 6 up to 59. So this is discrete in nature. And the CGPA typically, even to some extent, you can also call it, no, it's not. It is not also it is not also you know, it is also discrete to some extent.
Hypothetical one kind of.
Which one?
That's your one.
Third one, yeah. Even the CGPA is not continuous.
Because sir, I was telling earlier that is not a function, because for the mapping to be a function, we need all the elements in the domain to be mapped with the all the elements of the codomain.
Not all the elements. One element has to map to another element.
In the domain set, all the elements must be mapped, otherwise it will not be a function.
Not is depending upon the what is the range. Depending on the range. Huh?
Signal, there's no way it's told that signal is a function. That's what I'm telling.
Signal is a mapping. Yeah, it's to some extent it's a function also.
It is a function.
It is a function definitely.
And signal is always a function.
Yeah, it's a function. Yeah, it's a function. But you have to mention what is the the range over here.
Yes, sir.
That range you have to mention.
Yes.
Right. So yeah, it is also true that CGPA cannot be regarded as a discrete variable. It is also it is not a continuous. It is also discrete in nature. So now let me give you the example of say the average temperature within the last 60 minutes. The average temperature. That is continuous. Average temperature. That is continuous. So I record what is the temperature during the winter time. Say right at say 10 in the night. Say the temperature is recorded. Say at Dum is say 9.2 degrees centigrade. Right. So these are the things. So we have to understand now what is the basic difference between this continuous variable and this. Okay, well point raised. So is it okay up to this? Okay. So now let's move to, so after you understand these concepts, it is 4 different mapping: independent, dependent, continuous and discrete. Independent, dependent, continuous, discrete, continuous and discrete. Now let's move to some of the signal operations. Right, some of the signal operations. Before that, as I've told you, that signal is typically, as I've told you, signal is basically mapping from one domain to other domain, and most of the cases we will refer to time as the independent variable. Time as independent variable. Most of the cases. But make no mistake, the time is only one independent variable. So typically what happens? So if time is my independent variable, so I can record the signal, I can identify the signal as familiar, this is a familiar representation, x of t. X of t, what does it mean? That means this is a kind of signal, the name of the signal is x, and within bracket t, it signifies that it is a function of time. It is a function of time. So it can function on other variables as well. For example, this is an example of a one-dimensional signal. For example, if I draw the speech signal being rendered by any person over a period of time, it might look something like that. Audio signal being generated as a function of time can look something like that. So it's a function of time only. Say I have an audio clip of say 5 minutes, 300 seconds, 0 seconds to 300 seconds, and I just record this audio using a microphone, right? And how does it vary with time? So that gives you the variation. So this can be regarded as an example of a signal. Okay. Now, as of now, we have discussed, or we have mainly emphasized on a signal having only single dimension. Now let us try to identify any signal which is a function of 2 dimensions. Any signal, can you thought of any signal which is a function of 2 dimensions? Any 2-dimensional signal?
Sound wave.
Sound.
Depending on temperature and density of the surroundings.
Okay. Any other popular example? More popular example? Forget about the waves. Apart from that, I would like to have some examples which is not a function of time. Let's think of something which is not a function of time. If I consider an image, for example, say image of this dimension, say for example. So now the
position of a particle in a two-dimensional space.
Position, yeah. So what about the third dimension? I mean, two dimensions, you just mentioned the positions, that means x and y. Right. So I just captured the image. You know what is meant by pixel? Hopefully you understand what is meant by pixel. So I am dividing this entire image into, say, this many number of pixels. That means the picture elements. So let's assume that this is basically black and white image, grayscale image. Extreme dark to extreme bright. Typically 0 to 1 in this particular range. So the intensity value at any position, suppose the intensity over here, this intensity can be thought of as a function of this x and the y coordinates, x coordinate and the y coordinate. I call it f of x comma y. Suppose this is equal to 0.7. F of x1 comma y1, this is 0.7. That means what? At x is equal to x1 and at y equal to y1, the pixel intensity is 0.7 only. So pixel intensity is a function of if I call it, this is x and this is y, it's a function of the location. Pixel intensity is a function of the location. So if you have a two-dimensional image, so you have only two variables, x and y. Right? If you have a three-dimensional image, then you have the third dimension as well, x, y, and z. Right? So image can be thought of as a two-dimensional signal. And here the variables are the spatial variable. X is one variable, y is other variable for two-dimensional image. For three-dimensional image, what you have, 3D image, you have the x direction, y direction, as well as the z direction. Right. So now if I consider the black and white image, so for black and white image, what is happening? You have to understand the intensity, the brightness of that particular image. And you have only one value for that. 0 means complete black and 1 means complete white. For image, 0 stands for black, extreme black, and 1 stands for extreme white. And in between you have the grayscale, 0 to 1. Okay. So if I consider image as a signal, then you have what? Then you have in the domain set, you have how many variables? What is the dimension of the variables in the domain set? 2, x and y. Domain set. And in the codomain set, what is the dimension? So I have written sorry, r to the power n, hopefully I have written that time. R to the power n. R to the power n 2 c to the power m. So for image, for black and white image, this n turns out to be 2 and m turns out to be 1 for black and white image, right? For audio signal, if I observe this audio signal as a function of time only, so r is equal to your n is equal to 1, m is also equal to 1. Right? Now if I assume that my audio, the way I delivered my lecture, it's a function of time as well as it's a function of the ambient temperature. If the temperature is 20 degrees centigrade, this is something. If the temperature is even more, suppose it is 40 degrees centigrade, suppose the the loudness gets reduced because it's very exhaustive kind of thing. If your ambient temperature is very soothing, in that case your the loudness being generated from my vocal cord is even more. Okay, so now if I now plot the audio signal, the speech signal being generated by me as a function of the ambient temperature, if I have some mechanism which can record the temperature as well, apart from the time, then I can also you can also plot. So with respect to temperature, with respect to ambient temperature, room temperature, how does my speech signal vary? So in that case, I can consider okay, both of them. So it's a function of both t as well as the small t time and capital T temperature, and accordingly have two-dimensional variation. Now for the time, let's assume that this audio signal, speech signal is a function of time in front of. But for the image, it is a function of x coordinate as well as y coordinate. Two-dimensional image is function of x coordinate as well as y coordinate. So here, m is equal to 2 and m is equal to 4. Now suppose you don't have only black and white image. Rather, what you have some color image. Right? So color image is having three different components. They are known as the red component, green component and the blue component. And any color can be thought of as a combination of these three, red, green and blue. In RGB scale it is called RGB component. In HSI scale it is known as hue, saturation and intensity, something like that. Or YIQ also, sometimes. So let's assume that RGB. Okay. So any color can be thought of as a combination of the red component plus the green component plus the blue component. So if I consider a two-dimensional image, in that case n is equal to 2 and m equal to 1. And now if I consider two-dimensional color image, in that case your n is equal to m, n is equal to 2 and m is equal to 3. Two-dimensional color image, n is equal to 2 and m is equal to 3. Okay. Now let us consider, say, a black and white video. Black and white video. So video, as you understand, it's a function of time as well. Right? So at every point of time, you have certain intensity at particular location. So for video signal, and if it is a black and white, what about the n value? What is n? N is 3. What are those three? X, Y and time. And if it is black and white, then m is equal to 1. And if you have color video, in that case n is equal to how much? Color 3. No, n is equal to always 3. And m becomes 3 now. M becomes 3. Okay.
Last step on that.
This N3 M1.
N3 and M3.
N3 and M3. Okay. You have, say, color image, right? Color image means what? You have 2 dimensions. Image, you have 2 dimensions, X and Y, and you are placing frame after frame, and then the video gets generated. If you place the frames one after another, so that this persistence sufficient is maintained, so in that case, from the image itself, the video will be generated. Right? So the image that we are getting is a function of x coordinate as well as y coordinate. If I have 2-dimensional 2D image, x and y, and since these frames are produced one after another, so we have in the video we have the third element, I mean the third variable as well, that is the time variable. So x, y, t. These are the 3 independent variables. What about the dependent variable? Basically, it's a color. color image, a color video. So color means you have three different components: red component, green component, blue component. So for every x, y, and t, for example, if I consider x is equal to say 1, y is equal to say 1, and say t is equal to say 1, you have certain intensity, say 0.5. And if x is equal to 1, y is equal to 1, but t is equal to 2, at next time instant, suppose this intensity becomes 0.7. Now, if it is a black and white image, then this only one, 0.5, 0.7, only one. If you have color image, then this is basically you have three dimensions over there: red component, green component, blue component. So for every x, y, and t, you have three different R, G, and B. So 3 and 3. Is it clear now? Any doubt? No doubt. Okay. So mostly, once again, I am saying this for the n number of times that remember, signal is not a function of time always. Signal is not a function of time always. Signal is a function of any independent variable from where we are generating a dependent variable. But in our case, we will, most of the cases, we will refer to time as the independent variable. But don't let this recurring reference to time confuse you. You can also use the other variables, other independent variables, which you care to choose anytime. Right? So to start with, so let us consider some of the basic operations on the signals, and then we will go to the classification hopefully in the next class. So let's assume let's discuss some of the basic operations on the signals. And when I consider the operations on the signals, then come back to the square one and let's assume the signal as a function of time. Okay, the x of t. So x of t, not only function of time but also single dimensional signal. So let's make our life very easy. Don't get confused with multi-dimensional signal and all these things. Let's assume that n is equal to 1, n is also equal to 1. Okay, x of t, something like this signal. Very popular one, right? Sine of omega t, something like that. Let's come back here. But you understand what is there behind this. This is basically a representative of the inter-class signal family. This is not the repeater thing. This is only one piece of sample. Okay. So a signal is always associated with a dependent variable as well as the independent variable. In our case, x of t, what is who is the independent variable? T. Who is the dependent variable? X. Right. So whenever I do, if you just once again go back to the definition of signal, basically it's a mechanism that attempt to record, store, and communicate the information. So whenever you call it like store, sometimes the processing is also involved. That means you have to process the signal as well. And that gives you the basic understanding of signal processing. Right. So when it comes to the processing, so you can also process the independent variable, you can also process the dependent variable. So let's start with the processing of the independent variable, of the dependent variable first. Right, that is called the amplitude part, x. Let's process this. So x of t, so you have two types of processing. One is known as this amplitude processing. And second one is the time processing. Okay, I will come to that later on. Amplitude processing. So very basic operations you can consider. You have say y of t, that can be regarded as say x1 of t plus x2 of t. Very basic operations. The addition of two signals. It's very easy, no? Straightforward. x1 of t plus x2 of t. Addition operations. Or you can have like, so these are very fundamental things. Y of t, x1t plus minus x2 of t. You can have x1t or xt multiplied with some constant k, kxt. Amplification. Signal amplification. You multiply each of the elements by some constant. That is signal amplification or signal multiplication. Then comes y of t is equal to dxt dt. Differentiation, signal differentiation. Then comes, say, y of t is equal to signal integration. So this happens many times. You have two signals, you are adding, and you have the practical examples of that. Whenever I communicate the signal from the transmission side to the receiver side, some radio wave is being propagated. So you have the original signal xt, and along with that, you have some noise from the environment. So on the receiver end, you have the desired signal as well as you have the noise component. So the signal that I'm generating from the transmitter side is basically the audio signal, the signal that you like to communicate. But at the receiver end, what you are getting is not the actual signal. And apart from that, you are also getting the noise component. And because the noise gets added, sometimes the noise might be subtracted also. Noise is a random signal. We'll come to that random signal and the deterministic signal in the next class. So this the first example, amplitude processing, y is equal to x1t plus minus x2t, can be attributed to the signal reception at any receiver. This is a radio receiver. You have a radio receiver, and the signal that is received at the front end over there, this is basically the summation of two signals: the actual signal, the desired signal, plus the noise signal. Then the second example, y of t is equal to k times xt. Signal gets amplified. We do normally using an electronic amplifier. You have the subject analog electronics. They will study the analog amplifier and all, electronic amplifier. We would like to amplify the voltage range of the signal so that it can compete with the noise. So that the noise cannot affect the signal transmission, what we are doing, we are increasing the signal to noise ratio by amplifying the signal itself. So that is also done as a part of the signal processing. Then the third one, yt is equal to dxt dt. Can you give me some example? Where can you expect this yt is equal to dxt dt? Yt is equal to dxt dt. Can you give me any example? If you have an inductor there, and if you have the current, so the inductor is IT, and if the voltage is VT, so what is the relation between VT and IT? VT is equal to LDI. So for the inductor, the voltage current relationship basically is YT is equal to dx dt, that relation. So for every operations, you have some physical correlation with that, physical connection. And the last one, yt is equal to integration minus limit to t x tau d tau. What is the physical example for that?
So charge in a
Capacitor. What is the formula?
I is equal to I dot V to the power.
No, that's the formula. But minus limit to t x tau d tau. So what is that? So for inductor, what you have? Vt. For inductor, what you have? Yeah. So Vt is equal to L di dt, right? For inductor. And for capacitor, what is the formula? Vt is equal to 1 by c integration minus limit to t I tau d tau. Okay? So it follows everywhere. So this gives you the example of amplifier, electronic amplifier that you will study. And this is the signal reception. Signal reception. Right. So basically this amplitude of processing operations are more or less known to you. You know this. xt plus minus x1t plus minus x2t, x1t multiplied with some constant, and then you have this differentiation, then you have this integration, all these things. You know all these basic operations, basic mathematical operations, right? So this is all about the processing the dependent variable. Now comes processing the independent variables. And that is a little bit tricky. Hopefully you might not know this as of now, but we will learn gradually. Suppose I am having this signal x of t, right? And this is known as this time processing. I am writing time because I am using the time as my independent variable here. So for time processing, the first operation is known as reflection. That is hopefully new to you, unknown to you. Reflection. Reflection is one operation. So you have the signal x of t. You have the signal x of t, and you would like to generate x of what? Minus t. This is something new, now. X of t to x of minus t. What I mean to say is that suppose this is your signal t versus xt. It looks something like that. This is minus 1, this is 2, this is 0. This is x of t. And I would like to make it x of minus t. X of t to x of minus t. So how does it look like? So basically what you need to do is you take this axis t is equal to 0, x of minus t there. T is equal to 0 axis as the reference, as a mirror, and with respect to that you just take the mirror image xt to x of minus t. Then how does it look like? Minus 2 there, plus 1 there. Is that point okay? Reflection. That means we have not changed the signal amplitude. Signal amplitude was kept as it is. No change done. But the signal representation is different. That is all about the signal time reflection. Okay? Next comes, after reflection, next comes, that is very important, time scaling. Time scaling. So you have x of, right? And from x of t, I would like to have x of at, where a can be greater than 1 or a can be less than 1. One is known as upscaling, second one is known as a downscaling. How does it look like? X of t you have, I would like to have x of at. A is greater than 1 and a is less than 1. In one case, I will show you the upscaling case, upscaled version, and the second case I will show you the downscaled version. So suppose your x of t is something like that. This is t, this is x of t, and it's a triangular way -1 to +1, 0. That's the signal. Now, if I would like to have x of t to x of 2t, that means a is equal to 2. So how can I sketch that? You see here x of 1 is equal to 0 and x of -1 equal to 0. If you put t is equal to 1, that is 0, t is equal to -1, that is 0, right? So x of 2t, so x of 1 has to be 0. So 2t is equal to 1, so t is equal to half, right? So now if I plot x of 2t, then this is 0.5, this is minus 0.5, here it is 0. So the signal is compressed, right? So if A is greater than 1, signal is compressed. And on the other hand, if the value of A is less than 1, suppose x of t by 2, then the signal is expanded. Then it is something like that. Here you have 2, here you have 0, here you have minus 2. Yeah. So we have done first slide. You have done. I mean, the previous slide. What we have done? We have done time reflection. Then we have the time scaling. And remember these operations now that I am just referring. These operations are the building blocks of some more elegant operations that you will learn in next few classes. So time scaling, time reflection. Then you have time scaling, and then comes the time shifting. Number 3, time shifting. Time shifting. So what you have a signal x of t. So from that, I'd like to have x of t minus tau, where tau can be greater than 0 or tau can be less than 0. If tau is greater than 0, then it is known as delay. Shifting is having two different names. One is delay, second one is advancing. If tau is greater than 0, then that means the signal is delayed. So I have this signal. Let's consider this signal. This is t, this is x of t. And suppose the signal looks something like that. This is say 2. This is my signal. Okay, x of t. Now I would like to have x of t minus 1. This is t, and I'd like to plot x of t minus 1. That means tau is greater than 0. Tau is equal to 1. So same analogy. Here you see that x of 0 is equal to 0 and x of 2 is equal to 0. So there you have x of t minus 1. So t minus 1 has to be equated to what? 0. So t is equal to 1. And t minus 1 has to be equated to 2. That means t is equal to 3. So if you have x of t minus 1, that means this signal will look something like that. Shape remains the same. Only there is a shifting time. This is known as the delaying operation. Okay? And then the final one, for tau less than 0, what we have, we call it time advancement, x of t plus 1. That means t of minus or minus 1. Okay. Then how does it look like? Yeah. Sorry. Yeah. Suppose this is minus 1, this is 1, this is 0. Advancing. Time advancing. Okay. So when you consider the amplitude processing, addition, multiplication, or simple gain, scalar multiplication, and then integration, differentiation. So there you find that there is a change in amplitude value. There is a change in amplitude value. But the signal duration remains the same. If the signal is defined from 0 to 1, if x is defined from 0 to 1, then your dx dt is also defined from 0 to 1. Integration of x dt is also defined from 0 to 1, but the values are modified. Or k xt, the values are modified by some amplitude, by some 10 or 20, something like that. And for time processing, independent variable processing, what we have seen, the shape of the amplitude values, they are same. Only one change you can notice, that means the position gets altered. In reflection, there is a mirror image with respect to t is equal to 0 axis. Then you have what? Then you have the time scaling operation for a greater than 0 or rather a greater than 1. You have compressed wave. For a less than 1, you have expanded wave, time scaling, and then finally the time shifting x of t from x of t to x of t minus tau. If tau is greater than 0, then you have the delay, and if tau is less than 0, then you have that. And these operations, this reflection, sometimes also called folding. This folding operation. These different operations that I have discussed as of now, both the time processing as well as amplitude processing. Some of these operations will be used for the generation of one more elegant operation, which is known as the convolution operation. I don't know whether you have heard about the convolution or not. Hopefully not. Hopefully you have not heard about the convolution. So when we discuss the convolution, then it's kind of integration, but not exactly integration exactly. So then you'll see that in the convolution operation, you have these basic operations as this time reflection, then you have the shifting operation, then this multiplication operation as well as the addition operation. So these are the 4 building blocks of the convolution operation. And that forms the basis of your any LTI system that we have started at the very beginning, LTI system. So you'll see later on that these operations are very much essential. So you have to understand these operations. So as of now, anybody having any doubt regarding our today's discussion on the introductory lecture on signals and systems? No doubt. So that's great. So then I can conclude this lecture now.